discussing a presentation by Mikhail Lukin from Harvard. He is in the quantum computing space, and in particular, he works with Rydberg state atoms that he puts into an array of optical tweezers and then uses those Rydberg state atoms to do quantum error correction. So the concept here is that you have a system that allows you to manipulate physical qubits relatively easy and efficiently, and therefore create quantum error corrected logical qubits that then can be used for quantum computation. This is the Not Even Wrong podcast. It's October 29, 2024. This is Telco. For the day, we're down 1%. The market's up 20 basis points. For the year, we're up 31%. The market's up 22.2, outperforming by 8.8%. So this is an area that I've been following for years. Quantum computing is, in my opinion, the next frontier of computation. It's the next frontier for physical systems and understanding of physics, understanding of computation. So it's going to open a whole new world of understanding. I think looking back, once we have advanced quantum computers, we will probably think of our area as sort of the flat Earth area compared to what's coming in terms of just the depth and the possibilities and the opportunities that quantum computing will offer. Right now, we're still in a phase of figuring out how to actually create hardware that can support efficient quantum computing, and this presentation is in that sort of area. Now, Mikhail Lukin himself, he has, his background is applied mathematics from Moscow University or some sort of Moscow institute, and he's now at Harvard doing, research in multi-body systems that could be used for quantum computing. Now, let me lean back for a second and try to explain what that actually means. And let's start with, okay, what's the goal? The goal is to use the quantum nature of systems that have been observed ever since Max Planck developed the concept, and use the properties of quantum systems for computation. And one of the most important properties of quantum systems is the ability to interfere. So interference and entanglement. Those are the two things that can be used in quantum algorithms. So what are quantum algorithms? Quantum algorithms are algorithms that are specifically designed to take advantage of the properties of quantum systems. So now, Mikhail Lukin's work is primarily in the physics domain, but I would call it more physics engineering because he's actually building systems that can take advantage of quantum properties. Let's start with Rydberg systems. So a Rydberg atom, or a Rydberg state atom, is an atom, usually it's Rb, I don't know which element that is, but so it's an atom with a specific property that is chosen, if you excite this atom, you can put the electron, I guess it only has one valence electron, I assume. You can put that electron in a state where it's just far enough to not be really tied to the atom anymore, but not far enough so it's kind of loses. So we're not talking about an ion here. We're talking about, that's why it's called a Rydberg state, which is sort of a hybrid between an ion and a stable atom. And once that is created, you tweeze it into an optical tweezer, which is, think about it, you trap it optically so it can't go anywhere. And now you put a bunch of these things next to each other. They don't have to be too close to each other. But once you have a bunch of these Rydberg state atoms together, you can now have the electrons, which are kind of, think of it like loosely tied to the atom, but also kind of tied to the system. You can manipulate it with acoustic waves. You can manipulate it relatively easy and create systems that resemble quantum gates. Things like C0 gates, Hadamard gates, CC0 gates. That's the realm of quantum computation. That's the realm of computation, the theory of computation. People study, all kinds of different ways to take advantage of those things. But let's be very clear here what we're talking about. When we talk about quantum computation, We talk about physical systems that exhibit quantum properties, and then we talk about computational methods that can take advantage of those quantum properties. Fundamentally, what we're trying to do is do computation in a faster, more efficient way. Some things that can be done much faster, like for example, like I always say, the needle in the haystack problem is a real quantum computing problem. It's sort of a non-Clifford type problem because you can't do needle in the haystack problems very efficiently with classical computers, but you can do them potentially incredibly efficiently with quantum computers, because what the quantum computer would do is, instead of looking for the needle, it would just get rid of the haystack and therefore reveal the needle. That's the fundamental idea of quantum computing, which I like. I like this example because it illustrates the fundamental difference between quantum computing and classical computing. So what Mikhail's doing here is now he's created these Rydberg state atoms. He's put them into optical tweezers. That's a new technique. It's been around for probably maybe 10, 15 years, but it's really maturing, and there's a couple of startups actually working on this. What's really good about this, according to Mikhail, and the paper links in the show note, is that you can manipulate these optically trapped Rydberg state atoms fairly easily with low overhead, and therefore create logical qubits. And you create logical qubits by, let's say, having 50 physical qubits, entangle them, and then extract the information that statistically is probably more correct than not. In other words, you have 50 qubits that, say, are in the state X, and then 10 of them go wrong, but 40 are still in the state X, so you will statistically determine that the right state of these 50 qubits is X, and therefore use that in the logical qubit, and you could then use that logical qubit to do computation. And what's important here, you can have high fidelity computation. Of course, like in every other computation, you need to be sure that the fidelity is very high, that what you're computing is actually correct. Then you can create this GHZ gates, which are gates that are comprised of logical gates. So you could kind of build a scaffolding here now. You start with physical qubits, you create logical qubits, then you create logical qubit out of those underlying logical qubits. So you could build a scaffolding and increase the fidelity of each level of the logical qubits to the point where you have enough fidelity to actually perform quantum computation. This can be used for computation as well as, of course, simulation. That's always sort of the holy grail. So you could have a system evolve in certain ways using quantum simulation. For example, we could have multi-body systems evolve in certain ways, follow the evolution of a multi-body system, and then simulate, let's say, how atoms interact with each other or how molecules interact with each other. Of course, the more items we have in the system that evolves, the more complex things become. But again, fundamentally, we take advantage of interference and entanglement. Those are the two main characteristics of quantum computing that we don't have in classical computing, and therefore we can do massive parallel computations in certain ways. And there's the Clifford gates and the non-Clifford gates. Clifford gates are gates that can be simulated with classical computers. For example, Hadamard gate is one of those. And then non-Clifford gates are, CC0 gate, for example, cannot be simulated efficiently in a classical computer. So that's something that can only be done in quantum computation. So to summarize again, this is I occasionally talk about quantum computers. I know the field is relatively far away from realization. Unfortunately, I've started about 7 years ago looking into the space. I've done quite a bit of research. Went to conferences, went to summer schools, interviewed people, the whole thing, and it's becoming more exciting. I think the optical tweezers and the Rydberg state atoms seem to be a promising area. It's not the type of stuff that you would have expected from the beginning when we spoke about superconducting qubits or trapped ions and things along those lines. This is a little bit different, and I think the reason this is so exciting is because one area that physics has made a lot of advancements is in the sort of optical / matter interaction space. So when light interacts with matter, that's where I think physics has made a lot of good advancements, and this is a really good example. Rydberg state atoms and optical tweezers are actually exactly that. Light interacting with matter, and then we can use the properties of light and the properties of matter to create quantum systems, logical qubits, and then go and create quantum computation. Thank you.